So in the last video, we took a look at this theorem that stated that if the function f was ever differentiable at a point, if you could find the slope of its tangent line, then it would automatically be continuous at that point. It would be a connected graph at that point. Now, there are a couple questions that maybe start to arise immediately from this. Here's the first question. If a function is discontinuous at a, if it's not connected at a, could it be differentiable there? Well, this is actually kind of a weird logic sort of a question. Notice what we have up above. This says automatically that if a graph is ever differentiable at a point, then it guaranteed every time, no exceptions, must be continuous. So, if a function's discontinuous somewhere, could it be differentiable? I would say the answer to the question is no, because if it's ever differentiable, it has to be continuous. So we can answer number 1 by saying no. If f of x is ever, I'll abbreviate differentiable here with diff, but if it's ever differentiable at x equals a, it must be continuous at x equals a. So it's not possible to have a graph that is disconnected somewhere and differentiable at that point. So what that kind of means is that any time that I come across a graph where I maybe have a break in the graph, like we've seen sometimes in functions this semester, automatically at that break, I know the function is not continuous, and so automatically then it cannot be differentiable there. Because if it was differentiable, it would have to be connected. Okay, well, what about number 2? Number 2 is an interesting question. If a function is continuous at the value of a, must it be differentiable? So if a function is continuous, does it have to be differentiable? Well, notice that up above, this kind of says things in the opposite order. Notice here we're saying if differentiable, then continuous. And here we're kind of asking, can these things be flipped around? Now, this is an important time to note that we have to be very, very careful with how we read statements like this. Notice there is an if part and a then part, and that does not necessarily allow me to reverse the order. So I need to recognize that this is a very, very clear one-way statement. And so the relationship of the statement when these terms of continuous and differentiable are reversed is it's kind of up in the air. So for number 2, we have to say that we don't know. But the next example addresses this. So let's take a look at the next example to see exactly this sort of question. First, we're going to consider the function of the absolute value of x. We know and love this function. It's again one of our graphs to know, so hopefully you already have it dedicated to memory, but it's this nice V shape that we have going on here. Okay, so there it is. That's my y equals absolute value of x. And we should note, at least just by taking a look even at the picture, that the function is clearly continuous at x equals 0, right? The graph is connected there. So I want to go ahead and actually test this statement. If it's continuous at a spot, does it have to be differentiable? Well, remember, to test differentiability, we would have to calculate the derivative of our function and then see if we could plug in 0. All right, well, let's go ahead and see what we have for our derivative. So we'll say here that to find the derivative at x equals 0, we must compute the following. Okay, so let's see. To calculate f prime of 0, we would have to go ahead and compute f of 0, oops, sorry, I forgot my limit here, setting up my derivative, right? So I would have to go ahead and compute a limit as h goes towards 0. I would have to do f of 0 plus h, right now my x is a 0, minus f of 0 all over h. Okay, so we can simplify this down. All right, let's see what we come up with. In the numerator, notice I'm just going to have f of h. Well, f of h is just going to be absolute value of h. And f of 0 is really just going to be 0. So I'm going to be left with this, which of course just means I have absolute value of h over h. Now what's actually surprising here is that this is a limit that we actually already looked at back in a previous section. So I'll even put here, we evaluated this limit in section 2.3.1. And you could go back and take a look at this. We showed the following. We showed that if I was to do the limit as h approached 0 from the left side of this particular function, that I would end up with the value of -1. But if I did the limit as h approached 0 from the right side, I would get a value of +1. Now, I believe if you look back at section 2.3.1, you should be able to find this information. The only difference is that the limits we calculated there had x's and not h's, but that's just a variable switch, so it doesn't really matter. If I think, though, about then what this means, I could really say that because of this, or hence, the limit as h approaches 0 of this does not exist, right? I can't get an answer to this limit. But then what that means is that f of x is not differentiable at x equals 0. So apparently, the answer that we get to, if a function is continuous, must it be differentiable? Our answer to this question should end up as no, it shouldn't. So that's kind of strange. Just because a function is connected doesn't mean that it's going to be differentiable. But the theorem says if it's differentiable, then it must be connected. So I have to really try to keep those two directions straight in my mind. So this is kind of a strange set of ideas here. We can see that differentiability is tending to actually, or is failing here, because I kind of have this sharp corner that's kind of occurring in this absolute value. And there are actually many different types of ways that a function can fail to be differentiable, ways that would cause it to not be able to calculate, or would cause us to not be able to calculate the slope of a tangent line. One of those ways is something like a sharp corner. Another way could be the graph breaking apart. But in the next video, we'll take a look at a whole bunch of different ways that a function can fail to be differentiable.